Hey guys, my name is Tausif Kamal. I'm an 18-year-old AI developer. Today I'm going to be showing you how to implement the Monte Carlo reinforcement learning algorithm to play the game of Blackjack. And hopefully our AI agent will be able to win some money for us. So don't want to keep on waiting, let's get right into the tutorial. Okay, so I'm just going to quickly explain the rules for Blackjack so that we're both on the same page before going on to the coding portion. So basically the goal for Blackjack is to beat the dealer, meaning beat the casino. And the way to win is basically to get as close to 21 than the dealer without going over 21. So you're going to be dealt 2 cards and the dealer is also going to be dealt 2 cards. The only thing is there's going to be, the dealer is not going to be showing one of his cards while you're going to be showing all of your cards. And you can actually take 2 actions. Basically, you can choose to hit, which means to get more cards. Your goal is to increase your sum, right, in order to get as close to 21, or you can stick. Stick means to basically stay in your current position, not take any cards. So for example, if your current sum is around 20, you usually want to stick because if you choose to hit, then you're gonna just bust and go over 21 and you're gonna lose the game. So if the dealer gets closer to 21 than you're going to lose the game. If you go over 21, then you lose the game. The face cards are going to be counted as 10s, and the ace is either going to be counted as a 1 or an 11, depending on the current sum that you have. And then ace is basically considered to be usable if you can count it as an 11 without going bust. So for example, if my current sum is 3 and I have an ace or I get an ace by hitting, then that is considered to be a usable ace because I can count that as an 11. That's essentially it. Those are all of the rules that we need to know to code out our algorithm and really implement all of the actions and the states. So let's get coding right away. So first of all, we're gonna have to quickly understand. I'm just gonna give a brief overview of Monte Carlo reinforcement learning. If you actually don't know the algorithm itself, I suggest you to please just look at my article first. And then once you look at that article, I explain all the derivations of the equations, how we get each particular symbol, what everything kind of means. And then we're going to be implementing what I'm basically wrote in that article into here, onto the game of Blackjack. Also, there's a lot of other resources that you can use to really understand Monte Carlo reinforcement learning, and then you can come back and code the algorithm itself. So let's get started. So Monte Carlo reinforcement learning basically is just we're going to be averaging over returns that we're going to be getting from a bunch of episodes that we're going to be sampling. So the reason why we average over the returns is that unlike dynamic programming, in Monte Carlo reinforcement learning, we actually don't know this value. So this is the most important thing that we need to know to be able to solve the Bellman equation, which is basically the physics of the environment, the state transition probabilities. If you don't know this, we won't be able to solve the Bellman equation. And because Monte Carlo reinforcement learning is a model-free algorithm, we don't know the state transition probabilities, so we need to estimate them in another method. And one of these other methods is by averaging over the returns that we're going to be sampling from the episode. So this is a very useful cheat sheet, which you can basically get off of the Udacity Nanodegree RL program. But don't worry, this is all going to be linked into my GitHub. So if you do want to code out this algorithm, you can just go to my GitHub. Just clone this repository and then use a cheat sheet. Try to code out the Monte Carlo learning by yourself first. And then once you get the hang of it, then go into look into the solution that I'm going to be creating. All right, enough talking. So let's get coding right away. So we're going to be implementing algorithm number 11, which is basically the pseudocode for Monte Carlo control. But instead of first visit, we're going to be doing every visit. Every visit basically just means that we're going to be getting the returns, averaging the returns from every single time we visit the state. So we're just going to skip this step where essentially it just tries to get the return from the first state. For the first time that the state is visited, we're just going to be doing it for every time we visit the particular state. So let's get started. And basically, our goal is to get a win rate of around 42%. Because 42%, if you play using the basic strategy, which is basically one of the most optimal policies for playing blackjack, you'll basically get a win percentage of 42%. You can never like win consistently in blackjack because it's like a casino game. The casino always wins in blackjack, where essentially it's just gambling, right? So the highest rate that you can win by in blackjack, given that you play like perfect blackjack, is actually around 42%. So we're gonna try to get our most optimal policy to around 42%. All right. So now that we've gotten that out of the way, so I should just create a code cell above. I'm gonna do all of our imports. Import numpy snp, import gem, import from collections. Oh my god. Import default dict, import sys, import. What else do we need? Import JSON. You'll see why we're going to be needing all of these variables later on. I think we should be okay. Yeah, we also have to import some visualization functions. So from plot utils, import plot policy, and then plot win rate. So these two functions are just basically from the plot utils model that we defined here. So again, like all of the visualization functions are going to be in my GitHub repository. So you can just access this, clone the repository, get all the visualization functions. I'm not going to be explaining how we actually visualize everything because that's like a whole another concept right there using matplotlib. So you can just basically use these functions to visualize the win rate and visualize the policy once we actually do code out everything. All right, so this is going to be all of our imports. Let's actually do many more. Perfect. Okay. So the first step, we're basically going to be following the pseudocode. So as you can see in the pseudocode, it says to first initialize the Q values. So we're going to have to first represent our Q function. And so, okay, so let's do that. So we can first inspect the environment because we don't really know what it looks like yet. So we can just do gem.make blackjack version 0. Pretty sure it's version 0, yeah. And then we can do, for example, state is equal to n dot state reset and action space. Action space dot. Okay, so should be good. Let's print out the states and let's print out the action space. Okay, so once we actually get the states, this is basically the end of reset. It's just getting any state from the beginning of the episode. It's just a probability. So once we print out the state, we see that it's a 3 variable tuple. So basically the first element gives you the player sum. Player sum is basically, for example, let's say you have the card king, which is going to be represented as a 10 in the game of blackjack, and then you have a diamonds of 7. So if you add those two up, you're gonna get the total of 17. So that's essentially what the player sum is, and then this is the dealer card showing. So whatever card that the dealer has face up, that's going to be the card. So in this case, the dealer has the card of face up 2. And then finally, this is just if there's a usable ace or not. And then the amount of action that we have in blackjack is basically 2, which is basically to hit or to stick that we talked about earlier. When I talked about this earlier. All right, so once we've defined the environment now, that's good. So we need to think about how we're going to be representing the states. So what the Q function basically does is it's going to map states to 2 actions, right? So our states are 3 variable tuple states, right? So we're going to have 3 things that we're going to be representing a state as, and we're going to have to map those 3 things to a particular action, and there's going to be 2 actions. So mapping 3 things to 2 actions. And one of the ways that we can do that is through the default dict class from the collections module. So let me show you what I mean. So q is equal to default dict. We're going to define a lambda function inside of here, np.zeros 2, and then okay, no, that's basically it, 2. So let me show you what I mean. So for example, let's input a random state, m.state m.reset, not state. There we go. And let's print this out. So as you can see, this is just going to take any of a state, and any state. It's going to be like any state from Blackjack, and it's going to return us 2 actions. So we're either going to have action 0 or action 1. I'm referring to the indexes, by the way. So for example, action 0 could basically mean the Q value for getting a hit, and the action 1 could be the Q value for getting a stick. So in this case, we define these 2 actions, and this is how we're going to be representing the Q values for a particular action. This is one of the ways that we can represent the states and basically the Q function for the Blackjack environment. So then we're basically done. We just initialized the Q function for the Blackjack environment. So that's it for all states, for all actions. We have initialized the Q function. So next, what our goal is to define the Monte Carlo learning policy. So we can just say Monte Carlo control. We're gonna have to take in a few variables. So for one of them is num episodes. We're gonna have to take in epsilon. We're gonna have to take in epsilon minimum. I think there's gonna be a bit more. We're gonna have to take in alpha. So I'll explain what these mean just in a bit. Okay, so I think there's gonna be more, but this is good for now. So let's do our number of episodes that we're going to be training. Let's do 1,000,000 because 1, 2, 3. Let me see if I can count. Yeah, I think that's 1,000,000. Yeah, if it's not 1,000,000,000, that's I don't know. All right, so then epsilon to be initialized to 1, then epsilon min is going to be, say, 0.05. So again, with the epsilon greedy strategy, we never want to completely always take the greedy actions, because essentially we want to always leave a bit of the probability to take a random action, because this allows for exploration. Without this type of exploration, we might end up in a local minimum once we get to like the later episodes, and then we won't be able to always choose the most optimal actions all the time. So by setting this minimum value, we're able to always keep exploration viable for our agent, so that even if it's in like very late episodes, once the epsilon value has decayed a lot, it will still be able to take a random action 0.05% of the time. Actually, not 0.05%, it's just going to depend on the probability, but just a very low probability. So that's why we also set a minimum value. All right, so let's get coding our Monte Carlo control algorithm. So it basically says for I to num episodes. So we can just define this as okay, there we go. For episode in range 1 to num episodes plus 1. And we're just going to be doing this so that we can include the millionth value because of Python indexing, the way that it works. And okay, so first we're going to have to update our epsilon values. Epsilon is equal to, so this is how we're going to decay our epsilon value. So we're going to call the max, and we're going to do epsilon min and epsilon multiplied by a decay rate, 0.999. So we can just add on to this. So this basically means that every time this for loop loops, it's going to decay epsilon by 0.999. So it's going to take, so it's going to decay the epsilon value by like 0.00001% every single time this thing loops. And then after, for example, like 900,000 episodes, the epsilon value is going to be very low, and then we're going to be exploiting much more. Because when epsilon is very large, that means we're going to be exploring more, because the epsilon value is just pretty large. So this is going to make more sense once we actually code out the policy. So let's keep going. Next thing is to basically get a policy, define a policy using the epsilon greedy strategy. So this basically means we need to take an action based on our epsilon greedy policy from the Q function that we're going to be defining. So here we define the Q function. I think what could be better is that if we define the episodes first, and then inside that episode, we take the action. All right, so let me show you what I mean. So we need to define a function for generating episodes. And what I mean by this, we're going to have to return a few variables. So in this case, we're going to be taking the action regards to the epsilon greedy policy. So this means inside of here, we're also going to have to define a function for eps greedy policy. Then we're also going to have to, we're going to return states, actions, and rewards. So for each episode that we generate, for each episode, we're going to return the state that we've explored in that episode, the actions that we have taken in that episodes, and the rewards that we have gotten in that episodes. And then we're going to be using all of these variables in order to do the update rule of the Monte Carlo learning methods. Okay, so let's create a function right now. So def generate episode. What we're going to be taking in here is that let's define the Q values. Oops. Let's take this and let's put it in here. Perfect. We're gonna have to input Q, we're gonna have to input epsilon. What else? We're also gonna have to input the state, no? No, we're not gonna have to input the state. Yeah, that's good enough in here. So we're gonna have to define state is equal to m.reset. So every time that we actually run episodes in OpenIGM environments, we're gonna have to call the state function first in order to initialize a random state from the beginning of the episode. And then we're gonna have to keep track of the states, actions, and rewards that I mentioned. So we're going to be putting these three variables into a tuple. And in this tuple, we're going to be just putting all of these tuples in a list. And this list is going to be called episodes. So that's what we're defining, an empty list here. Next, we're going to have to get our action. Our action is going to come from the epsilon greedy policy. So I'm just putting that there to remind myself to define that function. And then once we do the action, then we're going to call into the next state, reward, done, and then info is equal to env.step action. So we're just basically calling the step function of the gym environment, and this is going to return as the next state that we're going to be ending up in, the reward that we get for transitioning into that next state, whether our episode is finished or not, and just extra information. So one thing that I forgot to do is we're going to have to put a while loop. So we can basically take multiple actions and multiple states in an episode, given that it hasn't finished. That's going to depend on the done variable, and then that's where we're putting the while loop so that we can range through multiple actions and get through multiple states if the done variable is false until the end of the episode. And the state is going to be equal to the next states, because essentially we want this to loop. The current state is going to turn into the next state, and then so that when it loops the next time, it's going to go into the next state. State is equal to the next state, and we're going to have to do episode. Yep. Append. So see, now you can now we can basically create that tuple that I talked about. State action, reward. Yeah. State, action, reward. So we're putting in the state, putting the action that we took, and we're getting the reward that we got. Next, we're gonna check if done is equal to true. Done is equal to true. No. Sorry, to do that, when done is equal to true, we're going to break. That's essentially it. And then we're going to just return the episode variable. All right, so that finishes up our part 1 for the Monte Carlo reinforcement learning on the OpenAI Gem environment. So we basically just created our function for generating the episodes, created our Q values, how we're going to be representing the states, looked at basically how the states get implemented in Blackjack, how the actions work, defining epsilons and all of that. And in the next episode, we're going to be defining our epsilon greedy policy function, and then we're going to be using all of these functions that we define in order to do the update rule for the Monte Carlo learning. And yeah, so stay tuned for the next episode. Peace out.